So we're going to move on to what our interest really with vector spaces was and why we're interested in vector spaces in the context of computer science. And this is an idea that is very widely applied. It's the notion of what's called a linear transformation, and this is huge importance in computer graphics. So, what's the sort of background we have to these? Linear transformations are a way of mapping between vector spaces, those objects that we saw introduced in the previous lecture. So in effect, what I mean by a mapping is we have some method, let's use capital T, and this method produces a vector V which belongs to some vector space, and the way it is using to produce that vector is from another vector U which also belongs to a vector space. So formally, the way we denote this operation, it's a transformation T which takes a vector in a vector space U and produces a vector in a vector space V. Now, U and V do not have to be different. They can be exactly the same vector space. So an example is the set of pairs of real numbers, which we saw in the previous lecture, defines a vector space. But it can also be different vector spaces. We can have one as a set of triples of real numbers and the other as a set of pairs of real numbers. Now, one example where this process occurs, where we are mapping from triples to pairs, is this operation of projecting objects which we think of as in 3 dimensions, but we have to show those effects on a 2-dimensional display screen. So in that case, we have to have some way of mapping between the two different vector spaces. Now, why are we interested in these? Why have I been emphasizing this method? Well, the very important use is in graphical effects in computer science. So these are things such as scaling, changing the size of an object when it's displayed on a screen. Processes such as rotating an object about an angle and displaying the outcome. And these we can very often implement, we can describe the process of calculation by means of some matrix and vector multiplication. So the vectors, these are corresponding to positions on a screen, to coordinates on a screen. And a graphical effect, for example, something such as doubling the length of a line when it's displayed. That's one example of a graphical effect. And we have an important correspondence relationship between this idea of linear transformation and matrix product. If an effect is a linear transformation, then we can describe it as the product of a matrix and a vector. It's also the case, however, that if we have some matrix description and we're multiplying that matrix by a vector, then the effect that is being described is a linear transformation. So a matrix vector product is a linear transformation. A linear transformation is a matrix vector product. I'll just give a quick overview of some basic matrix background, I'm sure people are already familiar with this from school. However, we are going to be looking at small matrices in this part of the course. So we have 2 by 2 matrices, which I'll typically describe in this form. So we have entries in the first row. We index the entries in a matrix by first of all giving the row and secondly giving the column. So for a 2 by 2 matrix, we have these 4 numerical entries. If we are multiplying a 2 by 2 matrix by a vector, then we can describe that by this process here. We take the 2 by 2 matrix and the vector, we produce the outcome of multiplying those two. We take the component x, we multiply that by the entry in the first row and first column. We add to that the result of multiplying the second vector entry, this component y, by the entry in the first row and second column. So this gives us the first component of our output. To obtain the second component of the output, we go through the same process, but with the second row of our matrix, we multiply x by the first entry in the second row, and we add to that the result of multiplying y by the second entry in the second row. For 3 by 3 matrices, process is very similar. Here's our general description of a 3 by 3 matrix. We have 3 rows, 3 columns. The individual entries in this matrix, we index first of all the row and secondly the column. So here we have the entry in the third row and second column. For matrix vector multiplication, if we're dealing with a 3 by 3 matrix, similar sort of process, we multiply corresponding entries in each row by going through the entries in each column. So for example, to get the second component of our output, we are multiplying the second row of this matrix. First of all, this entry to 1 by x, adding this entry by multiplying it by y, and finally adding the result of multiplying this by the entry in the second row and third column. In general, we have a very similar process for arbitrary matrices. For n by n matrices, we denote an arbitrary matrix using this notation. We enclose the value in the ith row and jth column in these square brackets. For multiplying an n by n matrix by another n by n matrix, we carry out this process of summing over all of the rows in the matrix the result of multiplying the kth entry in the ith row by the kth entry in the jth column. Now, we don't have to have exactly the same numbers of rows and columns in arbitrary matrices. We can have what are called non-square matrices. The other important property of matrix product is the result of multiplying a matrix A by a matrix B. In general, that's not going to be the same as a result of multiplying the matrix B by the matrix A. So let's go on and look in detail now at what I'm calling a linear transformation. What's the formal definition of these objects? Well, as I said, we have two vector spaces These can be the same vector space, they're not required to be different. And a mapping between two vector spaces, just recall formally we write in this style, that's said to be a linear transformation if it satisfies two conditions. The first condition is if we take any two vectors in our vector space U, say vectors P and Q, if we add those two vectors and apply the mapping to the result of that addition, that's exactly the same vector as first of all applying the mapping to one and adding it to the result of applying the mapping to the other. Recall that one of the properties of vector space is the result of adding any two vectors inside it is another vector in that vector space. The second condition, if we take any constant value in the underlying set of numbers we are using to define our vectors, and if we take any vector in our vector space, then the result of applying the transformation to the outcome or multiplying our vector by this constant, that outcome is exactly the same as a result of applying the transformation to our vector and multiplying the result by our constant value. So let's have a look at some examples of what I'm calling 2x2 graphical effects. One of the processes we might want to carry out is scaling an object by some constant value, by some real value. And we can do that by using a 2x2 matrix multiplication. We take the scaling factor S, we write that value along the diagonal entries, the other values of our matrix are 0, and so to obtain the result of scaling a coordinate by some factor S, we just multiply that coordinate by this matrix here. It's easy enough to check that gives the result we want. We have X multiplied by S, we add to that 0 multiplied by Y, we have X multiplied by 0, we add to that the result of S multiplied by Y. So we get this is our coordinate outcome. Rather more complicated operation, but also a very common graphical effect. Suppose we want to show the outcome of rotating a point anti-clockwise around the origin by some angle. We can do that by using this 2x2 matrix here and basic trigonometric operations. So here's an example of applying a scaling matrix. We have a square which has side length 1. We want to draw a square which is twice as large. So the outcome of applying the two-dimensional scaling matrix, it would replace this square by this square here. If we are looking at rotation, so here we have some point, we want to rotate that by an angle anti-clockwise. We apply the rotation matrix that I showed a couple of slides ago, and that will have the effect of taking this point here and moving it to this point here. Similarly, in 3 dimensions, we want to scale by some constant factor. We have a very similar looking matrix with a scaling factor written down the diagonal entries. We multiply that matrix by the coordinate we're scaling, and this is the outcome we get. Rotation in 3 dimensions It's quite a complicated process. I give the basic matrix on page 108 of the textbook. In practice, if we're carrying out object rotation in 3 dimensions, we're typically not going to do that by matrix operations. We use quite a sophisticated technique that, as I mentioned earlier, derives from one of the applications of what I'll call complex numbers. So here's an example of scaling. We have a cube with unit length sides. We want to draw a cube which is larger, whose sides are twice as large. And if we applied that scaling matrix on the previous slide, this would have the effect of taking what is drawn on the screen initially as this cube and subsequently display it, drawing it on the screen as this cube. Now, there is one slight inconvenience with linear transformations and a particular effect that we want to realize very often. This effect, which is called translation. So, a very basic operation is we have some object, which is at coordinates x, y, say, and we want to move that object to a new position. Similarly, we might want to carry out that effect in 3 dimensions. Now, if we look at the corresponding mapping between vector spaces that we're trying to define in this way, that corresponds to taking a vector, coordinates x and y, and moving it by adding some constant value to x and some constant value to y. And that mapping, that is not a linear transformation. We have a similar problem in 3 dimensions, the corresponding mapping where we take a 3-dimensional coordinate, we add one value to x, one value to y, one value to z. So how do we get around this problem? We use a technique which is called homogeneous coordinates. So what happens here? With homogeneous coordinate systems, we can implement 2-dimensional translation as a matrix vector product. We can implement 3-dimensional translation as a matrix vector product. But we do that using 3x3 matrices to implement 2-dimensional translations. So we take our starting coordinate and we add an additional component to it. Now this additional component isn't really important. What it's going to do is allow us to capture the effect of what happens when we translate a point. So the matrix we use is this 3x3 matrix, and the measures that we are using in our translation, if we want to move our point P places to the left and Q places upwards, these form the 3rd column of our matrix. Now if we look at what happens when we multiply our homogeneous coordinate x, y, 1 by this matrix, well, x multiplied by 1 is a value x, y multiplied by 0 is a value 0, 1 multiplied by p is a value p. We're adding these two values to get the position we want, and that gives a result x plus p, the coordinate we want to translate x to. Similarly, to compute the second entry in the coordinate, we have x multiplied by 0. That gives a result 0. We have y multiplied by 1. That gives a result y. We have q multiplied by 1, that gives q. We add that to y, and that gives the coordinate we want for the second component of our translation. This noise component, this value 1, that gets preserved in the homogeneous coordinate of the result because x multiplied by 0 is 0. Y multiplied by 0 is 0. 1 multiplied by 1 is 1. So when we add those three components together, we get the value 1. So what we've done is by adding an extra row and column to our two-dimensional matrix, we can do this for scaling as well. We can do it for rotation, and it turns out we can implement most effects in 2 dimensions just as the outcome of combining 3x3 matrix vector products. So for scaling, if we're using homogeneous coordinates, we would use this matrix. We just add this dummy row and this dummy column, and we have this value 1 in the homogeneous coordinate, and that gets preserved when we carry out the matrix vector product. Now if we want to combine effects, suppose we have a general scaling matrix, general rotation matrix, and a general translation matrix, then we combine effects in a single 3x3 matrix just by multiplying the matrices together. So we can carry out processes such as rotating an object, then scaling that object, then moving that object to its final destination. We have to be careful though, because the order is very important. The outcome, the result of moving an object, then scaling that outcome, that is not the same as a result of scaling an object and then moving it. And 3-dimensional rotation, as I've suggested, that raises some quite significant additional challenges.